In this Chapter 4 video, we're going to see how to solve what we call non-homogeneous second-order differential equations with constant coefficients. So here's our second-order differential equation with constant coefficients. We can see that it has a right-hand side f of t, which is not equal to 0. That's what makes it non-homogeneous. And to solve this problem, we have to split we actually have to solve first the differential equation a y double prime plus b y prime plus cy equals 0. And when we find that solution, we call that y sub h, the solution to the homogeneous differential equation. And then we have to have a specific strategy for finding the y sub p, called the particular solution, that solves the non-homogeneous right-hand side, and then the full solution of the differential equation we write as the homogeneous solution plus the particular solution. So on the next blackboard, we're going to see how we find that particular solution, or how we start off with the structure of y sub p so that we can solve for y sub p. So let's assume that our second order DE with constant coefficients looks like this, and that the right hand side has an exponential function, e to the rt. That exponential function is multiplied by a power of t, and then there's some constant out front. In that case, we would set the particular solution y sub p. It would contain a part of it, that is the e to the rt. This t to the m part here in our right hand side would require that we have a polynomial of degree m multiplying e to the rt, and then we may also need to multiply that by this function of t to the s. The power of s would be determined as follows. So we would have s equals 0, this s and the t to the s out front here, if r is not a root of the homogeneous DE. So s equals 0 if e to the rt is not a solution of the homogeneous DE. S equals 1 if e to the rt is a single solution of the homogeneous DE. And s equals 2 if the e to the rt is a repeated solution of the homogeneous DE. Remember, we have repeated solutions when both roots are the same. So let's look at an example of the first case where the s is 0. So let's consider this non-homogeneous differential equation that has three possible right-hand sides. First, let's form the characteristic equation of the DE, which is r squared plus 2r minus 3 equals 0. That factors as r minus 3, or actually r plus 3, r minus 1 equals 0. So the roots are minus 3 and 1. And so the homogeneous solution, the solution to the 0 differential equation, this differential equation with 0 right-hand side, is c1 e to the minus 3t plus c2 e to the t. So notice that this y sub p, this first case here, the r equals minus 3 is a root, whereas in this case and this case, r equals, well actually in both those cases too, the r equals 1 is a root. So what's the y sub p going to look like in the first case? So we call this case A, case B, case C. So for case A, the y sub p would be, well, it has to have the e to the minus 3t part, but it also has to have that t to the s part because minus 3 is a root, and that power of s is 1, right? Since this is a single solution, so this would be a t plus b, right? This structure right here with the m equaling 1, so it just has this term and this term. In the case B, yp still has to have the e to the minus 3t. It has to have, because of this this is not right in this first case. The y sub p would be, it starts off with the e to the minus 3t, and then it has to have a t to the power s equals 1. So it's this case right here has to have the t to the s out front. It doesn't have this part right here because there's just a constant out front. So it would be just this e to the minus 3t multiplied by t. In this next case, the B case, we have this 3t out front of the e to the t, so it is this case right here with m equaling 1, so it has this term and this term as well. Because e to the t is a root, it also has this t to the s part with s equaling 1 because it's a single root. So if we put all that together, we've got what, a t plus b, and then it has to be multiplied by t to the s, with s being equal to 1. And then the third case, the yp would also have the e to the t part. Because of this t squared part, it needs an at squared plus bt plus c, a polynomial of degree 2, and because e to the t is already a root, it needs a t to the first part here. This right here was with the e to the t, so this one should be e to the t. So here are the three possible y sub p's. So let's solve the case A first. So our differential equation is this. So here's our differential equation. We already said y sub h is c1 e to the minus 3t plus c2 e to the t. Because the right-hand side has a e to the minus 3t in it, we said that yp equals e to the minus 3t so it's e to the minus 3t, and it has to be multiplied by a power of t, because that's already a root, and that power, since it's only a single root, is 1. So it's t to the first, or just t. So what we need to do is calculate yp prime by the product rule. So it's first times the derivative of the second, which is minus 3t e to the minus 3t, plus the derivative of the first times the second, which is this, and then yp double prime would be differentiating both terms, first times derivative of the second here would be what? 9t e to the minus 3t. The derivative of the first times the second would be minus 3 e to the minus 3t, and then the derivative of the second term would also be minus 3 e to the minus 3t. So we want to combine this information together to have it solve the differential equation. So we're going to multiply yp times minus 3, yp prime times 2, and y double prime isn't multiplied by anything. And so if we combine those together, we get what? So we put together here the left-hand side of the differential equation. This is the minus 3 y. This is the 2y prime, and this is the y double prime. Here, here, and here, and we're going to add all that up and set it equal to 5e to the minus 3t, the right hand side of the original. So when we add up this first column, we just get a 0 here, and in the second column we get a minus 4e to the everything that we had here originally should have been multiplied by a, because we need to find out what that constant is. So put an a there, and an a here. And so we still get a 0 here. So we've added everything up, and we get minus 4a e to the minus 3t equals 5 e to the minus 3t, so minus 4a equals 5, and a equals minus 5/4. So in this, for this first differential equation, we get y equals yh c1 e to the minus 3t plus c2 e to the t. That is our yh plus our yp, and the yp was minus 5/4 t e to the minus 3t. Because, as we saw, our yp had to have this structure to it, and so we had to find that a, which we found was minus 5/4. And then the general structure is yh plus yp. So you can see finding the undetermined coefficients can be fairly complicated. Finding the derivatives, combining the derivatives together, and solving is not that simple a task. If we were to do the same thing for the case B, you can see that it's going to be more complicated, because differentiating this here is going to, first derivative, second derivative, and combining it together is going to be a little bit more difficult to do. So in this second case, yp was t times at plus b e to the t, and so it is at squared plus bt times e to the t. We need yp prime, at least when we differentiate the e, the t part, it doesn't have a constant. So first times derivative of the second is just the function itself. And then the derivative of the first is going to be what? 2at plus b e to the t. And if we combine all that together, we get what? at squared plus b plus 2at plus b all multiplied by e to the t. And then yp double prime would be that same thing, at squared plus b plus 2a times t plus b times derivative of e to the t, which is e to the t. And then the derivative of the first is what? 2at plus b plus 2a times e to the t. And if we combine that together, we get what? At squared plus b plus 4a times t plus b, or 2b plus 2a e to the t. So you can see we've got, when we combine all this together, we're multiplying what? Y double prime times 1, yp prime times 2, and yp is times minus 3, because it must go into this differential equation right here. So let's see if we can do that, combine that together. So if we multiply by minus 3, we're going to get minus 3at squared from here. We're going to get 2at squared from here. And we're going to get 1at squared from here. So we just have 0at squared. And then if we do the t part, we've got what? bt here, or minus 3bt from there. We've got 2b plus 4a times t from here, and then from down here we've got b plus 4a So we're just left with what? The minus 3b and the 2b and the b cancel out, and the 4a and the 4a combine together to give 8at. And then if we do the constant, we've got what? ab from here, and then 2b plus 2a from the last, or it's b times 2, so it's 2b from here, and 2b plus 2a, so it's 4b plus 2a times e to the t, and we were setting that equal to the right-hand side, and the right-hand side in that case was what? 3t e to the t. So if we write that a little differently, 3t e to the t plus 0e to the t, and we equate like coefficients, we see that the 8at must equal the 3t, so 8a must equal 3, and a must equal 3/8. We also see that the 4b plus 2a must equal 0, so 4b plus 2a must equal 0. Plug in a 4b plus 6 must equal 0. 4b equals minus 6, so b equals minus 6/32, or minus 3/16. So if we combine all that together in the structure of our yp, this time our yp looked like this. So at squared plus bt times e to the t, so our yp is going to be the structure at squared plus bt times e to the t, and we just found out that a was 3/8 and b was minus 3/16, so 3/8t squared minus 3/16 t e to the t is our yp, and yh, or y, equals yh plus yp. Yp is right here, and yh we already knew was c1e to the minus 3t plus c2e to the t. So a fair amount of work to get these, no question about it, especially when we have to multiply by powers of t. Let's do one more example. Let's start with the same differential equation on the left side, y double prime plus 2y prime plus 3y, but let's make the right-hand side equal to sine of 2t. There, because yh is the same differential equation we've used twice before, c1e to the minus 3t plus c2 e to the t, it's not going to interfere with the yp. What's the structure of the yp? Well, in general, it would be the same as what we had before. In case A, it would be a t to the s and a m t to the m plus dot 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 plus a0, and then that would be times cosine beta t plus, same thing, t to the s b m t to the m plus dot 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 plus b m sine beta t. But we get lucky in this case because out front here we just have a constant a, and so we do not need this part or this part or this part or this part, and so our yp would just be a cosine, and the beta is 2 plus b sine 2t. So we differentiate it. So there are the derivatives, and when we combine them together with 3 of yp and 2 of yp prime, let's see here, the cosine terms are multiplied by what? Minus 3a and 4b and minus 4a, and so when we combine all that together, we get and then the signs are going to be what? Minus 3b minus 4a and minus 4b, and so that would be what? Minus 7b and minus 4a, so minus 4a minus 7b sine of 2t, and the right hand side was sine of 2t. So that gives us two equations. minus 7a plus 4b equals 0, and minus 4a minus 7b equals 1. Multiply the top equation by 4 and the bottom equation by minus 7. So we get what? Minus 28a plus 16b is 0. And multiplying the bottom by 7, or minus 7, so we have 28a plus 49b equals 7. Combine those together, that's what? 65b equals 7, or b equals 7 over 65. And that would give a equals 28 over 65 divided by 7. So that would be what? 4 over 65. So yp would be 4 over 65 cosine 2t plus 7 over 65 sine of 2t. So there we worked 3 examples of undetermined coefficients. The last one was actually the easiest one, and we will continue this with working more problems in the classroom of this type. So this concludes this video on the undetermined coefficients method.